Since the energy crises of the 1970s, there has been a running joke in the physics community. Commercial nuclear fusion is 30 years away, and it always will be. For 5 decades, that joke held true. Researchers made steady, incremental progress, but the timeline to a grid-connected reactor remained stalled for half a century. The stagnation makes sense when you consider the sheer scale of the ambition. Scientists are essentially trying to build, ignite, and contain a synthetic star right here on Earth. To do that, they rely on a machine called a tokamak. A tokamak is a massive, donut-shaped reactor designed to trap hydrogen fuel heated to over 100 million degrees using invisible magnetic cages. The timeline stalled because human engineering hit a brutal physical wall, trying to control an environment that actively destroys its container. At 100 million degrees, plasma doesn't behave nicely. It is highly turbulent, chaotic, and completely nonlinear. The ultimate threat to this delicate balancing act is a tearing instability. A tearing instability is a catastrophic event where the magnetic field lines holding the plasma together suddenly rip apart. When those lines break, the glowing plasma escapes in a matter of milliseconds. It slams into the reactor walls, instantly cools down, and kills the entire fusion reaction. For decades, engineers tried to manage this chaos using traditional, linear computer models. But human-coded software lacks the speed to catch a millisecond-level collapse. Recently, the market reached a sudden tipping point. Over $7 billion in private equity has flooded into the fusion sector, with startups now targeting grid-scale power by the early 2030s. The physics of the star didn't change. The timeline suddenly compressed because we finally developed a tool that processes information fast enough to tame the plasma: artificial intelligence. This leap forward started when premier physics facilities like the Princeton Plasma Physics Laboratory began collaborating with AI leaders like Google DeepMind. They tackled the plasma problem using deep reinforcement learning. This AI training method learns to make complex decisions by trial and error to maximize a specific reward. Researchers fed this algorithm decades of historical, real-world fusion data. When deployed inside active reactors like the D3D National Fusion Facility, the AI approaches the problem differently than past systems. It actively predicts the chaos before it happens. This chart shows a dual timeline comparison. On the top timeline, the AI detects the precursor signals of a tearing instability up to 300 milliseconds in advance, while the human-coded timeline below crashes when the instability hits. Using that 300 millisecond head start, the AI takes autonomous control. It rapidly shifts the shape and intensity of the reactor's magnetic coils. By instantly adjusting the magnetic pressure, the AI squeezes the turbulent plasma back into a stable state, preventing the disruption. By providing the reactor with superhuman reflexes, AI has overcome the biological limitations that held back magnetic confinement for decades. But real-time control is only one part of the equation. AI is pulling the design process out of the physical world and into digital twins. A digital twin is a highly accurate virtual replica of a physical system that updates itself in real time using live sensor data. Historically, engineering a new reactor component required months of supercomputer time just to calculate how plasma turbulence would react to a slight geometry change. Today, modern physicists instead use AI surrogate models. This lightweight algorithm is trained to mimic the exact outputs of massive simulations, but it delivers the answers in milliseconds. Beyond fluid dynamics, researchers use artificial intelligence to identify novel alloys capable of surviving extreme heat and neutron bombardment inside the reactor core. These algorithms work in tandem to optimize the entire plant's architecture before any steel is cut. By digitizing the trial and error process, AI has transitioned fusion from an unpredictable physics experiment into a solvable engineering problem. Because of this algorithmic acceleration, scientists are no longer waiting on fundamental discoveries in physics to move forward. The industry's entire focus has shifted to scaling up manufacturing and optimizing the engineering required for grid deployment. This means the old joke, the perpetual 30-year wait, is officially broken. Heavily funded startups are currently assembling the complex hardware of physical, commercial-scale pilot plants. Tech giants like Microsoft and Google have already signed binding offtake agreements to purchase fusion electricity in the 2030s. This massive, multi-billion-dollar influx of private capital and corporate contracts confirms fusion's transition into a manageable engineering market. There is a deep technological paradox driving this market reality. The explosive growth of AI and cloud computing demands an absolutely massive scale of electricity. Data centers are drawing so much power that this insatiable energy appetite threatens the continued evolution of artificial intelligence itself. In a poetic symbiotic loop, the massive computational power of AI provides the physics solutions and material discoveries required to fuel its own future. AI-accelerated fusion promises an era of clean, firm baseload energy, requiring zero fossil fuels and producing no long-lived radioactive waste. For the first time in history, artificial intelligence has transformed the prospect of bottling a star into a scheduled commercial deployment.